Hi students, in this video we are going to talk about the limit comparison test, and then after that we're gonna talk about the guidelines for choosing a test. So let's first look at the statement of the limit comparison test. So let summation an and summation bn be series with positive terms. So keep in mind that you need positive terms here, and define L is equal to limit of a sub n over b sub n, where n goes to infinity. So this is definition of L, and we're gonna conclude the pattern of convergence by looking at the value of L. So if your L is strictly positive, it means L greater than 0, then your conclusion of series AN and series BN go in the same way. So it does mean that summation AN and summation BN either both converge or both diverge. That is the conclusion number 1. So this is the case that you usually want to see because it is easy. So you want to get the value of L to be strictly positive. So once you have L greater than 0, then your conclusion for summation A sub n and summation B sub n are the same. So you see that this is super easy to use in example. If not, you have other two cases. So if L equal to 0, this is a bit harder because you need more condition that your summation of Bn is convergent, and then now you can conclude that summation of An is convergent. And the last one, if L is equal to infinity and you know that summation Bn is divergent, then summation An is divergent as well. As I told you that most of the time you're gonna end up with case number 1. So this is the one that you need to memorize because you're gonna face this case a lot. So now let's move to examples so you can see how the limit comparison test work. So before we start example 19, so let me give you the idea that usually what we have is the problem gonna give you summation of A sub n, and then you have to pick your B sub n by yourself, and then after that you apply the limit comparison test. Alright, so example 19 part A. So use the limit comparison test to check the convergent pattern of the following series. So let's start by part A. So we have summation of 1 over 2 to the n minus 1. So for here, so I am going to let my an to be 1 over 2 to the n minus 1. So clearly that this is a series with positive terms, right? Because it's always positive, because once you plug in n equal to 1, n equal to 2, and so on, the term an always end up with the positive thing. After that, we need to choose our Bn, but we are going to skip the part of choosing Bn first, and then we will come back later. Let's move on to the part that we need to compute L, which is the limit of A sub n over B sub n, where n goes to infinity. So this thing gonna be limit of, well, A sub n is 1 over 2 to the n minus 1, right, where n go to infinity, and I need Bn as well, so I need this thing times 1 over Bn, right? So how do I pick Bn? So I need to pick Bn such that I can compute this limit easily, right? So what I am going to do is I'm going to pick my Bn to be 1 over 2n. So this is also positive, right? Because 1 over 2n is always bigger than 0 when n is bigger than or equal to 1. So once I choose my bn to be 1 over 2n, so I can replace this thing by 1 over 1 over 2 to the n, right? So you can see that this is tricky. So I pick 1 over 2 to the n because what I want to do after this, I want to just make the limit easier to compute. So after that, I have 1 over 2 to the n minus 1 over 2 to the n. And then after that, I have limit where n go to infinity of 1 over 1 minus 1 over 2 to the n. And then after that, you can see that when n go to infinity, this thing go to 0. And then at the end, I have 1 over 1 minus 0, which is 1. So come back to the statement here. You can see that when your L is equal to 1, that means your L is bigger than 0. And this falls into the case number 1. So summation an and summation bn either both converge or both diverge. So because we pick bn to be 1 over 2n, so summation of bn gonna be summation of 1 over 2n, right? And the summation of 1 over 2n here, this is convergent because this is a geometric series with r equal to 1/2. So that means summation of an and summation of bn are both convergent. This is by the limit comparison test. Well, to sum up, summation of 1 over 2 to the n minus 1, where n start from 1 to infinity, this is a convergent sequence. So you can see the big picture of the limit comparison test here. So the idea is you need to pick your bn by your own, right? And then after that, you're trying to compute the limit. And once you get the limit, well, you use the result that you have in the box here from the statement of the limit comparison test. So most of the time, you're gonna fall into the case number 1, that summation of an and summation of bn, they are both convergent or both divergent. Alright, so let's do more examples. So example 19 part B. Alright, for this question, so we're gonna let an to be our 2n to the 4th power minus 2n squared plus 1 over 3n to the 6th minus 1. So this thing is always positive, right? Because, well, the term that we have minus sign is so small. So this is always positive. And then after that, well, let's skip the part that we need to shoot bn first because we can come back later. So bn equal to something that we don't know yet. So we're gonna do the limit comparison test first. So let L to be limit of a sub n over b sub n where n go to infinity. So this is limit of, well, I have an here, so I'm gonna put 2n to the 4th power minus 2n squared plus 1 over 3 to the 3 times n to the 6th power minus 1. Alright, so the idea is I need to multiply 1 over bn as well. So we need to pick bn smartly so we can just, compute limit easily. So here, what I'm gonna do is, because I see my series I see my term in the limit here that I have n to the fourth power and I have n to the sixth power here. So if they are both degree 6, so we can compute limit easily. So what I'm gonna do is I'm going to pick my bn to be 1 over 1 over n cube. So it's gonna be easy to compute limit. So I will pick my bn to be 1 over n square. So this is always positive for sure. And then let's compute the limit first. So this part I am going to have limit of 2n to the 6th power minus 2n to the 4th power plus n square over 3n to the 6th power minus 1. So you can see that what I did is just I multiply n square to the top, so I get this thing. And now this is super easy to compute the limit, right? Because you can divide everything by n to the 6th. So this is going to be 2 minus 2 over n square plus 1 over n to the 4th power and then over 3 minus n 1 over n to the 6th power. So here I just divided everything by n to the 6th power, right? And then now I have 2/3 at my limit because this go to 0, this go to 0, this go to 0. And then once I get 2/3 as my limit, so you can see that this thing is bigger than 0. So it means summation of an and summation bn are both convergent or are both divergent. So we need to come back and check, well, from bn here, so what can we conclude about summation of bn? So summation bn is going to be summation of 1 over n square. So this thing is convergent by p series, right? This is p series where p equal to 2. So that means this thing is convergent. So by the limit comparison test, so you can conclude that summation of a sub n, which is 2n to the 4th power minus 2n square plus 1 over 3n to the 6th power minus 1, this thing is also convergent. Alright, that's example B. So I know this is not easy to use because there are so many steps. Alright, so let's do 2 more examples. So let's do part C. So suppose that we have summation of 1 over 2n minus square root n. So I am going to let my an to be this thing. Alright, this thing is bigger than 0. My bn, I'm gonna save it for later. So let's come back later for that. And then now let's compute L, which is limit of a sub n over b sub n. Alright, and that thing is limit of 1 over 2n minus square root n, where n go to infinity. Then I need my bn as well, so I can compute the limit easily. So here, because I have polynomial 2n here, so I need one more n on the top, so you know it can balance it, and then I can compute limit easily. So what I'm gonna do, I'm going to pick my bn to be 1 over n. And for this reason, so I am going to have 1 over n here. And that will return me limit of n over 2n minus square root n, right? And that I can divide everything by n. So I have n over n on the top. The bottom I have 2n over n minus square root n over n. And this thing going to be limit of 1 over 2 minus 1 over square root n. Easy, because this thing go to 0 when n go to infinity, and this is just 1/2. So it means your L is equal to 1/2, that is bigger than 0. So by the limit comparison test, an and bn well, summation of n and summation bn go into the same pattern of convergence. So we have bn here equal to 1 over n. So summation bn, this is going to be summation of 1 over n. This is p series where p equal to 1, or you can say this is the harmonic series. So it is divergent. That means by the limit comparison test, we conclude that summation of an, which is summation of 1 over 2n minus square root n, this is also divergent because the answer here must be the same answer of the convergent pattern of B, summation Bn. Alright, let's move to the last example. This is the one that is a lot harder compared to all previous question. So let my an to be logarithm of n over n square. So it is harder because this is the logarithm term. Alright, now I need to choose my b as well, right? So my bn, I have to choose to be something. So let's skip that part first, and then let's compute our limit L. So it's gonna be limit of a sub n over b sub n. Alright, so I have limit of log n over n squared. Well, what should I pick for bn so I can compute limit easily? So you can see here that it is not easy to compute limit of limit of this thing. So let me first try to choose something like well, let's say that I'm gonna pick bn to be 1 over n squared. Alright, and see what happened. So if I pick this thing to be 1 over n squared, so I have 1 over n squared. And then I can cancel this thing. So what I'm gonna have left is I have limit of log n, which is infinity. No, I don't want this thing, because if your L equal to infinity, you need more condition that your summation b sub n must be divergent too, right? Because if you have your L to be infinity, so you need that your bn must be divergent too. Well, your summation of bn must be divergent too in order to conclude something about an, right? So if you take step back, go to the statement here, you can see that, well, when L go to infinity, you need that summation of bn must be divergent too. So you can conclude the pattern of summation an. But here, well, bn is convergent for sure if you choose 1 over n squared. So this bn does not work. So we're gonna choose another bn. Well, this is the hardest part for the limit comparison test, because you need to choose bn wisely so you can compute limit easily. So for this question, I'm gonna give you the answer immediately. So what are we going to do is we are going to pick your bn to be 1 over n to the 3 over 2. It is amazing that, well, the number are gonna cancel perfectly, so you get something good at the end. Alright, so we're gonna choose bn to be this thing, which is greater than 0 for sure. Alright, so I replace my bn to be 1 over n to the 3 over 2, right? And then something cancel, so I have limit of logarithm of n over square root n, right? Because this thing cancel one time, so I have square root n. And then after that, I can use the L'Hopital rule. So I have limit of n go to infinity. So differentiate log n, so I get 1 over n. Differentiate square root n, so I have 1 over 2 times square root n. So here we Note that we extend the domain first and then we apply the L'Hopital rule. Apply the L'Hopital rule. Well, I still use the same notation n. Well, but keep in mind that this limit can be computed because we extend the domain. Alright, so after that, I simplify this thing a little bit. So I have limit of TikTok, I have limit of 2 over square root n, right? After you simplify it, where n go to infinity, because I move 2 up to the top, and then 1 over n and 1 over square root n cancel, so you get this thing. And then after that, you have this thing to be 0. So you have your L is equal to 0. But luckily, you have your Bn to be this thing. So this thing imply that summation of Bn is convergent, right? Because this is P series where P equal to 3 over 2. And that means by the limit comparison test, so by the limit comparison test, well, we conclude that summation of a sub n, which is log n over n square, must be convergent as well. Alright, and that wrap up the limit comparison test. Now you have learned a lot about the test for the convergence of a series. So now you may get overwhelmed that how do I pick the test to use for each question? So this is the rough guideline for you. So let's look at this thing together. So we gonna say that to check that summation of an is convergent or divergent, we can follow this step. So the first one, why don't we begin with the divergent test? Because this is the easiest one. So if you can show that your limit an is not equal to 0, then you can conclude that the series diverge. Otherwise, you can just move to another technique. So number 2, if you feel like divergent test does not work, so you can look at the series and check if there is a special case. So it could be a geometric series. So if it is a geometric series, so the series gonna be converged when absolute r less than 1. Otherwise, it will be divergent. So if it is P series of the form 1 over n to the P, so this thing gonna be convergent with the case that P is bigger than 1. So otherwise it will be divergent. So check also if there is a telescoping series. Alright, so the case number 2 is the one that you see the specific pattern. So if not, you can look at the general term of the series. So if the general term of the series looks like something that you can integrate, then you can use the integral test. But keep in mind that the integral test is tedious, because in order to use the integral test, you need to check 3 conditions and then you have to integrate it. So try to avoid the integral test as much as possible, unless I force you to do the integral test. Alright, so number 4, if your general terms contain something like n factorial, n to the n, a to the n, something like that. So you could try the ratio test, because the ratio test gonna look at limit of a n plus 1 over n, and that will give you a lot of cancellation if you have n factorial n to the n or something like a to the n. Well, on the other hand, if you have a series with n in the exponent, so maybe you can use the root test, right? Because if you have something like right, something an, right, and then you have something raised to the n power, so when you do the root test, you have to take the n root, and that will mean you raise to the 1 over n power, and this thing gonna cancel. So you have something that is easy to compute limit. And the last case is if your general term cannot match with any of the above things, so maybe you can try comparison test or the limit comparison test, but this is hard to use. So well, this is the last thing that you should check, but well, let's try number 1, 2, 3, 4 first. But if it does not work, so you can move to comparison or limit comparison test, which is a lot harder for you because you have to pick your bn, or you have to pick something to compare. All right, let's start by looking at question 20 here. So we have a mixed practice for you. All right, example 20. Use the test of your choice to check the convergent and divergent pattern of the following series. Let's start by part A. So I have summation of n to the 100th power over n plus 1 factorial. So for sure, if you see factorial here, you should use the ratio test. So I say that this must be the ratio test. So the trick is here. If you see factorial, well, it is recommend that you're going to use the ratio test. It is recommend that we use the ratio test. Alright, to use the ratio test, we're gonna compute limit of an plus 1 over an, right? This is our ratio test. Well, the ratio test gonna work when the series has only positive terms, and then you can see that, well, this thing has a positive term because if I let an to be n to the 100 over n plus 1 factorial, this thing is always positive, so ratio test works. Alright, so let's compute this thing. So it is limit of, well, let's start by replace n by n plus 1, so I am going to have n plus 1 to the 100 power over n plus 2 factorial. Alright, and then my an here, this is just 1 over n to the 100 over n plus 1 factorial. Alright, let's see how it cancels out. So n plus 1 factorial gonna cancel with n plus 2 factorial. So you have just n plus 2 left. Alright, so you have limit of 1 over n plus 2. And then I am going to group the thing that we have n plus 1 to the 100 and n to the 100 together. So I have n plus 1 over n to the 100. And then this is limit where n go to infinity of 1 over n plus 2 times 1 plus 1 over n to the 100. Alright, and then when n go to infinity, so this thing go to 0, right? And then you gonna have 1 plus 0 to the 100, so you have 1 here at the end. It's goes to 1. This thing goes to 0, right? Because where n go to infinity, n plus 2 go to infinity, and 1 over infinity is 0. So at the end you have 0 times 1, which is 0. So when the ratio test has limit of a n plus 1 over a n equal to 0, which is less than 1. So by the ratio test, you can conclude that summation of n to the 100 over n plus 1 factorial, this thing is convergent. Now let's move to part B. So for part B, we have a sub n equal to n squared plus n plus 1 over 4 n squared plus 1. So what should we do with this thing? So you can see that we don't have factorial. So we don't have something raised to the n power. So ratio test and root test could be super tough to use. So it doesn't look like we can integrate this term easily as well. So integral test would be hard to use. Well, maybe we start from something simple like the divergent test. So let's compute the limit of this thing. So the limit of this thing is going to be limit of n squared plus n plus 1 over 4n squared plus 1, where n go to infinity. And you can see that on the top I have n squared here. This is the highest degree. In the bottom I have 4n squared here. This is the highest degree. So I can divide it everything by n squared. So I have 1 plus 1 over n plus 1 over n squared. So I divided the top thing by n squared. I divided everything on the bottom thing by n squared as well. So I have 4 plus 1 over n squared. And then this go to 0, this go to 0, this go to 0. So at the end I have a quarter. And that means the limit is not equal to 0. So by the divergent test, we conclude that summation of a sub n is divergent because it is not equal to 0, right? Easy like that. So the divergent test is easy to use. Every time you compute the limit and then you get something that is not equal to 0, so it's gonna be divergent by the divergent test. This should be the first thing you check when you see the problem. Alright, so let's do part C. So let's try divergent test first. See if we can compute this limit 2 to the n over e to the n minus 1. Right? Let's compute this thing first. If the limit is not equal to 0, then we can just use the divergent test. Well, if I compute this limit, so what I'm gonna do, I'm gonna just divide everything by e to the n, right? Because this is the biggest term in the bottom two. And then after that, I have limit of 2 over e to the n, and then I have 1 minus 1 over e to the n. So this thing gonna go to 0, this thing go to 1, this thing go to 1, and then 2 over e is something that is less than 1. So if you have something less than 1 raised to the n, this go to 0. So your limit gonna be 0 over 1 minus 0, which is 0. Well, so the limit of an is equal to 0. So you cannot apply the divergent test. So the divergent test does not work for this question. You see the point? And then after that, once you see that the divergent test does not work, but luckily you can see that you can fix this thing a little bit by using the limit comparison test. So if you have your an to be 2 to the n over e to the n minus 1, So this is your limit of we need limit of an over bn. This is our L. So if you let your an to be just 2 to the n over e to the n minus 1. Now I am going to pick my bn to be 2 to the n over e to the n. So here when I have an over bn, so I'm gonna have 2 to the n over e to the n minus 1 times e to the n over 2 to the n. The reason why I pick bn like this because I want to balance thing when I compute limit, and then you can see that 2 to the n cancel, and then after that I have limit of e to the n. Well, I move e to the n to the bottom right away, so I have 1 over e to the n minus 1 over e to the n. This thing is limit of 1 over 1 minus 1 over e to the n. And this thing goes to 0 that I mark it 1 over e to the n. So I have at the end 1 over 1 minus 0, which is 1. Well, this thing is bigger than 0. So by the limit comparison test, an and bn gonna have the same pattern of convergence. So this thing, summation of bn is summation of 2 over e to the n, right? And then this is convergent, right? This because this is the geometric series. Geometric series with I equal to 2 over e, which is less than 1. So this is convergent. Well, to conclude this thing, so you can say that by the limit comparison test, the summation of 2 to the n over e to the n minus 1, this is convergent as well because the result must be the same thing with bn, summation bn. Alright, so let's do the last part, part D. So here we have an equal to n square over 3 to the 3 times n square plus 1 to the n. So this is obvious that you need to use the root test because you have something raised to the n power here. So to use the root test, you can just compute your rho, which is limit of the n root of an. Right, and this thing is going to be limit of the n root of an, which is n square over 3 to the 3 times n square plus 1 to the n. And this thing cancel, so you have limit of n square over 3 n square plus 1 at the end. And after that you can just divide it n square on the top and the bottom, so you have 1 over 3 plus 1 over n square. This thing is 1/3, which is less than 1. So by the root test, summation of n square over 3n square plus 1 raised to the n power here, this is convergent. And that sum up this example. So you can see that the hardest part for series is you have learned so many techniques, and when you face a problem, you have to pick your technique by your own. And that is the hardest part that you have to practice. So good luck all, and then we're gonna see you in the next video on section 1.6 alternating series.